So again, here we have two equations of lines. I'm not really happy with the forms that they're written in, so I'm going to take the time to rewrite them. My vector equation of line L, I have a 5, a 3, and a 0. And here the parameter is s. And this x-coordinate has a -4. The y-coordinate has a 1. Z-coordinate has a 2 with the s. And my second line has a -3, a 7, and a 6. The parameter is t. We have a -4 with the x, a -1 with the y, and nothing with the z. So now we have lines in 3 dimensions, and apparently they cross. We have to find out what the position vector of these 3-dimensional lines are, because they cross somewhere. In order to do that, we look at the parametric forms of each equation. So we've got, from our first equation, we've got 5 minus 4s is equal to x. Our y-coordinate is 3 plus s. And our z-coordinate is just going to be 2s. From our second line, we also have our x-coordinate is -3 minus 4t. Our y-coordinate is 7 minus t. And our z-coordinate is always 6. What this allows us to do, does it make sense? If they have a common point, the x-coordinates would have to be the same. The y-coordinates would have to be the same. The z-coordinates would have to be the same. And what our parametric equations allow us to do is to make 3 equations that 5 minus 4s has to equal -3 minus 4t, because the x-coordinates would have to be the same. Our y-coordinates, 3 plus s, would have to equal 7 minus t. And our z-coordinates, 2s, would have to equal 6. We make a system of equations. We have 3 equations and only 2 unknowns. So we have more information than we need. We could solve this with matrices. We could solve this with substitution or elimination from the past. You get to decide by looking at it what would be the easiest thing to do. Yeah. Now, of all those equations, this one is pretty straightforward to say. I think s has to be 3. I'm pretty sure. So now that we know s is 3, we could plug that back into either of the other 2 equations. In the second equation, you would get 6 equals 7 minus t. That seems like less mental math to do than plugging it into the first equation. But if I would do that, I'm going to get t is equal to 1. And just to make sure that it works, okay, and this is important, because if we don't plug that s value and that t value back into the first equation and find out that it works, it actually means those lines don't intersect, which is more likely. 2 lines in 3 dimensions more likely don't intersect than they would intersect. So if I plug in 3 for s into my first equation here, on this side I'm going to get -7. And if I plug in 1 for t on this side, I get -7. So it does work for all 3 equations. So they intersect when t is equal to 1 and s is equal to 3. And since we checked all three equations and it does work for all three of them, we know that those answers are correct. Now to find out that position vector, we can either choose to plug in t equals 1 or s equals 3 back into our equations. Notice what happens when I plug in t equals 1. I'm going to get negative 3 plus negative 4, negative 7. I'm going to get 7 minus 1, 6, and I'm going to get 6. If I had used my first equation and plugged in s equals 3, 5 minus 12, negative 7, 3 plus 3, 6, 0 plus 6, 6, negative 7, 6, 6. So that is the position vector where they intersect. Now that we figured out that these two lines in 3 dimensions intersect at a certain point, we can figure out the angle between those two lines as well. So we know that this point at negative 7, 6, 6 is where they intersect. One line is going in some direction over here. Another line is going in some direction over here. And we're trying to find out this angle in between. Now we learned the other day that cos of an angle is equal to the dot product between two vectors divided by the length of each of the vectors. And all we have to do is decide which are the correct two vectors to use to figure this out. Because we have a bunch of vectors figured out here. In each of our equations, we have two vectors. And we've also got our position vector of where they intersected. So we've got 5 to choose from. You could just randomly choose 2 of them and take your chances, a 1 in 10 chance that you will pick the right 2 and go from there. Or we could think about this and say, how do we decide which 2 vectors we're going to use? So I've drawn, I extended them there so you can actually imagine 2 lines. And we have to think, what are these vectors? Going back to our equation here, this is a point. The first ones are always points on our graph. And the second one, these second 2, these are the direction that they're going. So now thinking of our intersection, are those red arrows best represented by a point on our graph or by the direction that those lines are going? By the direction. So we have to use our direction vectors. So our direction vectors, going back here, were negative 4, 1, 2. And our other direction vector, negative 4, negative 1, 0. So now cos of theta, the dot product would be multiply the components, negative 4 times negative 4 is 16, plus negative 1, plus 0. The length of our first vector would be 16 plus 1 plus 4, be square root of 21. And our second one will be 16 plus 1 plus 0, square root of 17. Simplifies to 15 over the square root of 361 minus 4, is that 357? And now to find our angle, we just go to cos inverse of 15 over the square root of 357. Question doesn't say degrees or radians, so we can do either one. My calculator's in degrees right now. 37.45. If you use degrees, you have to use the degree sign. If you use radians, you don't have to have any symbol. You can write radians if you like.